Okay, we're going to go ahead and get started. Thanks everyone for joining us. This is the research results presentation for uncontrolled concrete bridge parapet cracking performed by Dr. Norbert Delot at Cleveland State University. If you are watching on the web and you have a question during the presentation, please send your questions, email them to research@dot.state.oh.us. The final report for this project will be available on the research website in the next couple of weeks following this presentation. For those of you in the room, if you have questions, please hold them until the end of the presentation. Other than that, Dr. Delot, it's all yours.
Okay. Again, good afternoon, or whatever time it is if you're watching this later on the web. Professor Norbert Delot, Cleveland State University, and of course, I didn't actually do this work. This was a student study done by Jeff Bezos, who's graduated, and some continuation work with Amy Caliban, who worked with him, and Lauren Hedges. And they would like to be here today, but they're currently, as you'll see at the end, they're currently actually out on a bridge looking at this issue. And I think this particular photo, which we'll come back to in a little bit, gives you an idea of the problem we're trying to address. And essentially the problem that we're trying to address is this. ODOT District 12, and it's probably not unique to District 12, ODOT, or the U.S., observed that there was some widespread premature cracking of concrete bridge parapets. And it shows itself in a number of forms. You have vertical cracks that occur between the joints, and in some cases you have horizontal cracks that occur at the level of the top bars in the reinforcement, and then some, maybe slightly harder to classify cracking patterns. We've kind of referred to those as map cracks, and then again some spalling of cracks or joints. So just a common picture of vertical cracks. You don't see any joints in the picture. We're in between joints, and we have a couple of cracks that have formed in between the joints. Those are the typical vertical cracks. And the funny thing about this is something I'd never paid any attention to before, and now I can't stop seeing it. Like on the drive down, I'm always looking at all these parapets and looking where the cracks are and so forth. Those are the vertical cracks, and then these are the horizontal cracks that occur roughly at the level of the reinforcing steel. It seems like a change in the design has, by and large, hopefully dealt with this problem. And that was a change from 2 number 5 bars at the top of the parapet to a single number 6, and that doesn't seem to give you that horizontal cracking problem. The vertical cracks don't seem to pose much of a safety issue. This is potentially a remote safety issue if this is over a highway, an interstate, for example, and the horizontal cracking progresses to the point that a piece of concrete falls loose and comes down. Very remote possibility, but it could happen, and it could have severe consequences. And of course, from an engineering standpoint, it's very difficult to deal with things that are low probability but high consequence. This we refer to as map cracking. It's really a combination of horizontal and vertical cracks. And there are a couple of things I want to show in this particular slide that I think is relevant. You can see on top of the parapet we have a vandal protection fence. And off here, if that shows up to the right, we have a vandal protection, the base plate for the VPF post. Okay, we'll call it that. Actually, I went through, and in this presentation, we actually have better pictures in the report, but I did not include one in here. But one typical feature we often saw was that we had cracks propagating down from the VPF, and that could be because that provides an inclusion in the concrete and a crack initiator that works down. Here on the left side, you can see a typical sawn joint. One thing that you can see is it doesn't quite go all the way to the bottom. It's kind of difficult to take a saw and get it all the way to the bottom. In fact, you really can't possibly get completely all the way to the bottom. And then we have vertical cracks pretty close parallel to it. Well, what this may suggest is that the sawn joint never in fact cracked, and that instead the crack is acting as the joint. And when we got out and in the field and started taking a closer look at that, I think we found a little bit more supporting evidence that that was perhaps what we were dealing with. Spending some time on these because these are really the best photos that we have of this. And in some cases we had some light spalling near the joint problems. Now, one issue, of course, is how potentially damaging these types of problems are. There is potentially a safety issue associated with the horizontal cracks, probably not much with the vertical cracks. Maybe the main problem with the vertical cracks is simply that they are aesthetically unpleasing, which I guess is a scientific way of saying ugly, but you can paint over ugly, and if that's our biggest problem, then maybe we don't have too many issues in terms of long-term performance, realizing that in modern construction, the rebars that might be exposed by the cracking are epoxy coated. But basically our scope, this is what we were given from District 12, is that there were a number of bridges they observed throughout District 12, and literature review found that there were other issues in other states. And 4 specific bridges were identified for this study. And the idea was that we would take a forensic engineering approach and look at these 4 bridges in great detail and see if we could come up with a list of hypotheses and try to come up with what the most likely causes of the cracking of these bridges might be. And these are all bridges that cross interstates or other major highways. Jennings Freeway, for all intents and purposes, is an interstate. So Canterbury Road over I-90 in Westlake, Wagar Road over I-90 in Rocky River, Sheldon Road over I-71 in Middleburg Heights, probably, I think that might have been about the worst one we looked at, and Spring Road over Jennings Freeway. Nice thing about these bridges, because they were overpasses, is it was relatively easy. In many cases they had sidewalks. It was relatively easy to get out on the parapets and get real close and do close observations and do some tests. Obviously, if you're talking about a bridge that is actually an interstate highway, then getting out and looking at that parapet is going to be much more challenging. And of course, you can really look at them really only from the inside. And we tried to look at timelines, because the timelines potentially can give you clues as to whether there have been changes in specifications and procedures that might have had some impact of these. And all the 4 bridges that we studied at the time were either built or rehab in terms of a deck replacement, which also included the parapet replacement in the range of 10 to 15 years ago, starting with Spring Road 97, and then the other 3 were rehabs in 99, 2001, 2002. One thing that you can't really answer when you're looking at bridges that are 10 to 15 years old is if you see a crack, was that crack there a week after the bridge built, or did it just pop up a year before we got out? You don't know roughly when, or even approximately when it might have created a problem. Well, they are ugly. One of the main issues is we took a look at the economics. When you replace a bridge deck, of course, you have to replace the parapets with it at the same time. On the other hand, if a parapet deteriorates to the point where you have to replace the parapet before you're going to do a regularly scheduled bridge deck replacement, then that cost is basically wasted, because the next time you have to do a bridge replacement, you're going to replace the bridge parapet as well. So that's something that we want to avoid in terms of the economics of the problem. And in addition to District 12's observations of this issue, they had one case study where they did do a parapet replacement in 2002. It was a bridge over I-271 that had excessively cracked parapets, and the cost of doing that, the parapet replacement itself, which didn't include ceiling, fence repairs, and expansion joint repairs, was approximately $140,000. So later on, when we go looking at alternatives of what we might change in terms of parapet design or construction, we want to keep some figure in mind of what the cost might be. And so first you look at that number and say, well, if you can maybe, if it's a change in construction costs and it's maybe $100,000, you don't consider the time value of money, then maybe it's a good investment. But I got to thinking on the way down, because when you drive from Cleveland to Columbus, you have a little time to think, that you really need to be thinking in terms of the expected value of per bridge. And what I mean by that is let's say 1 in 20 bridges needs a premature parapet replacement. Then you multiply that by 5%, and you get an expected value, expected cost per bridge is $7,000. And then if we make a change that costs $20,000, then maybe it's not economical. I just pulled 1 to 20 out of the air. I have absolutely no basis for that number. On the other hand, if it's 1 out of 1,400, a very rare and a relatively large population of bridges, then your expected value is $100, and it doesn't make a whole lot of sense to do anything. So when we get to the next project and we look at what we might do and what things might cost, that's something to keep in mind. For an expected value of $100, you really can't do anything else. And of course, a basic principle of undergraduate engineering economics is you always have to consider the do-nothing alternative. And in fact, we may need to consider the do even less alternative, because if it turns out that most of the time the saw-cut joints we put in parapets don't work at all, then maybe a recommendation would be you eliminate them altogether and avoid the costs of making those cuts. And essentially then you're adopting the same philosophy of a integral abutment bridge or a continuously reinforced concrete pavement, where you don't put in a joint and you assume that the steel is going to handle the performance of the crack over time. And it's pretty well known that generally concrete cracks, and the real issue is not whether or not you have a crack, but what the performance of the crack is over time and whether that leads to excessive deterioration that causes replacement. Clearly in this case it did, and one of the things that I'm thinking now we may end up doing is we may want to get some idea of what the frequency of early parapet replacement is in various ODOT districts, and therefore what ballpark we ought to be in when we talk about the cost of solutions. But again, that's just from this morning and not fully developed yet. So our objectives were to try to determine the causes of parapet cracking and identify applicable measures for repair and prevention, and make recommendations to ODOT to help reduce the life cycle costs. And one of the things is caused by the prematurely cracked parapets. And one thing to think about is if you improve bridge deck design and construction procedures such that a bridge deck lasts longer, and therefore the life cycle cost of bridge decks goes down, all of which would be a good thing, you might start to run into a larger frequency of premature parapet replacement, because now your parapets are no longer lasting as long as, shall we say, improved bridge decks. So our basic premise was to adopt a forensic engineering approach, or if you want to call it that, sort of the Sherlock Holmes method, which was you list all the possible causes and then you take the facts and you eliminate those that are contradicted by the facts and you see what's left. If you're really big with this, then you start throwing in all ridiculous hypotheses, but we pretty much stuck to the likely hypotheses for causes of parapet cracking. So in the report, when it comes out, you'll find an extensive list of hypotheses, and then the field evidence that we use to decide that certain hypotheses were unlikely or least likely or could be eliminated. We hope to identify a comparison bridge. In the course of this study, we really didn't come across, as you'll see, any suitable comparison bridge, but we're looking at some future work where we will hopefully have some real comparisons. And then a desk study, a literature review. Is this who has previously encountered this issue and what do they do about it? Reviewing plans and reviewing inspection records to see what kind of information might show us. Once that was developed, then the next task was to do site visits to each bridge and record the field observations. A major part of this was crack measurement and mapping. For each of the parapets, determining where the cracks were and how wide each crack was. And Jeff and Amy went to bridges during the summer and also during the winter. And what we were interested in looking at is, do you have a weather-related change in crack width? In theory, at least, in winter, a crack should open up wider because the bridges, the colder temperatures cause it to crack more, and make those comparisons. In fact, we really didn't see a significant effect. And then the other thing about the cracks is how tight are they? Because it's recognized that there are some relationships between the width of a crack and the likelihood that you'll get deterioration over time. We want to compare the construction plans to the as-built conditions, and they seem to have been built the way that the plan showed, which was good. And we also wanted to do some non-destructive evaluation. The main forms of non-destructive evaluation that we use and that we're using on the continuation are we have a James R-meter rebar locator, which will give you depth to reinforcing steel. One of the things that we wanted to determine was whether the steel was closer to the surface or further from the surface as indicated by the plans. Closer to the surface may be higher risk of corrosion, although not so much for epoxy-coated bars. Further from the surface, maybe you've got the steel doesn't do as good a job of controlling cracks. So we wanted to see from that how deep the steel might be. And also ultrasonic pulse velocity, essentially putting a wave through the concrete. And I think that's going to be more useful in our future studies than it was in this. And then taking those facts and observations in the desk study, try to identify what the most likely causes were, and to develop some possible solutions. This probably actually came from the interim report on this, where we were at some point, so probably not relevant much anymore, but we did the literature review, developed a list of hypotheses, got the documents, then the background case studies, and then the next step was to actually execute the site visits. And I believe there were a minimum of 2 site visits per bridge, warm weather and cold weather. Unfortunately for the students, I don't think we ever sent them out in nice weather, but February 2012 on a bridge in Cleveland can be, you want to dress warm. Anyway, so they gathered field observations, took a lot of digital photographs. There are a lot in the appendix of the report to document what the observations, and those crack measurements, as we talked about. Over the course of the year of observation, did we see additional cracks form, or were the cracks from September 2011 to February 2012 essentially the same cracks you saw before? No new cracks are forming. Are the cracks relatively tight, and then between those 2 times, are they increasing in size? And again, we didn't really find a good comparison bridge. What we did find is that not all of the bridges, I would say, were equally bad, and you could argue that the bridges that weren't quite as bad maybe provided a useful comparison to the worst of the bridges. The other thing we wanted to do is we wanted to look at findings from other state DOTs. And one concern we have, and it's kindly, I guess, sort of paid out, is that you don't find a lot published on this topic. I think if you go into the, what's it now, the TRB database, and you do a search on bridge deck cracking, you'll get tons and tons and tons of stuff. If you do a search on bridge parapet cracking, you get the papers on bridge deck cracking that included parapet somewhere in the keywords. There just doesn't seem to be a lot published out there. We did find some work from Illinois, from Michigan, and Connecticut. We did find some other research studies, one on early age cracking of concrete barrier walls, and that is documented in the report. Studies on slip form construction of parapets talk about this a little bit more, but one way that some states, agencies have reacted to parapet cracking problems is by banning or restricted slip forming. And obviously the people who make slip forming equipment then want to do some studies and try to find out if it's their equipment or something else. There's also the issue of the structural contribution of parapets, and of course there's a lot of information out there on cracking of concrete bridge decks, which may or may not be relevant. Now, one thing we also looked at, I don't know that we talk about it elsewhere in here, is if you have a vertical crack in a parapet, and that lines up and corresponds to a crack in the bridge deck, then you can expect that that is due to the crack in the bridge deck propagating up through the parapet, because if the deck is cracked, the parapet is not going to hold the bridge together. And so in that case, there's nothing from the standpoint of the parapet that you can really do. You're going to get that crack. So there is some, I guess, some relationship between the two. Probably the maybe the most in-depth was from the Illinois Department of Transportation. Roughly 10 years ago, FHWA and Illinois DOT put together a joint process review on bridge parapet construction because they also had uncontrolled vertical cracking in recently constructed bridge parapets. Maybe one difference from some of these studies from what we did is we were looking at relatively old parapets, 10 years old or later, and these were some that were maybe right after construction. They thought that perhaps one cause might be inadequate spacing of the control joints in the parapets, poor consolidation when using the slip form method, and they issued the temporary moratorium on slip form construction. Hence, you'll later see Gameco does a study on the same topic to try to address these issues. 2007, they developed the Guide Bridge Special Provision number 61, and that lifted the moratorium when you had some certain restrictions, and they basically put a lot more specs on the slip form operations, limiting the speed, terms of continuity of parapet reinforcement, looking at glass fiber reinforced polymer reinforcement, I guess GFRP reinforcement, replacing steel with glass fiber polymer rebar, some stricter tolerance limits, and tighter restrictions on curing procedures for the parapets. Michigan DOT published a study in 2007, studied how that related to changes in design and standard practice. They identified a number of factors that they thought that changing the design or the profile of the parapet to a more solid face design had a greater risk or trapped more snow and trapped more de-icing chemical. When you trap snow in Michigan and Ohio, you're not just trapping snow, you're trapping, I guess what I would call a salt snow cone that then melts up against the parapets. They also thought that using the slip form might have exposed the concrete to higher shrinkage stresses. And they also thought that there might be a problem related to the use of high absorptive aggregates, which kind of contradicts some work we did a few years back on high absorptive aggregates making bridge deck concrete more resistant to cracking. So I'm not sure how the laws of nature change when you cross the border, but you never know. One of the difficulties in doing this type of research is it's incredibly difficult to try to control for variables, so there's always a lot of things going on. Connecticut Department of Transportation also had an increase in parapet cracking, and they had something called a paraffin-coated joint, which we may want to look into more detail. Get to where we're going with this later on. And so they changed back to the paraffin-coated joints in order to reduce that cracking. So essentially, what you have, based on whether you're in negative moment regions near a pier or positive moment regions in between, is that you actually have a paraffin coating that breaks the continuity of the concrete. Whereas with a normal saw joint, what you're trying to do with the parapet is you're cutting into the concrete around the edge, and you're hoping that it cracks then between the cuts in the same way that it does in a concrete pavement joint. But I think for a number of very good reasons, it's a whole lot easier to get a concrete pavement joint to crack in the right place than it is because you've got a dowel that allows slippage, than to get a parapet to crack the way you want to. There's also some work in Canada, in Quebec. Fortunately, they seem to have published it in English as well. They found a lot of transverse cracking. They believe that the cracking often occurred within the first 48 hours of the concrete placement. They're looking probably earlier. They're not looking 10 or 15 years later, so this is an interesting finding. So maybe one of the things we would look at is, maybe one thing is to look at what happens the day you pull the form off. What do you see? They identified possibly high cement content that might contribute to heat. Also, high cement content, you also have high paste, maybe high water content. All those lead to higher shrinkage. Another theory they had was that you had traffic vibrations prior to adequate strength development of the concrete. Not likely to happen on a new bridge, but if you're redecking and you're doing half the bridge at a time, then if you're maintaining traffic on the other side when the concrete's green, potentially those vibrations could give you some problems. And they also looked at issues of thermal gradients due to the use of different formwork material on either side of the barrier, which gets us to wondering what causes the cracking. And there are two factors, well, three factors potentially. Potentially tensile structural stresses, if those are present. The concrete's always going to have shrinkage that will put it in tension. And if you have a temperature drop, particularly combined with shrinkage, that temperature drop could be associated with cracking. So one of the things we're doing in future work is we're going to be monitoring temperatures right after construction. As you'll see, Gamaica Corporation did a study of parapet wall cracking. I don't know that they did a report, but Jeff found a presentation that they had made. And if you look at the timeline on this, you'll see that it's in between the Illinois moratorium and when they lifted the moratorium, so you can see that what they were doing was trying to come up with ways that you could do slip-forming paving without having the cracking problems. They suggested perhaps a little bit less reinforcement because too much congestion. They were concerned about, of course this kind of goes the other way, having the rebar cage be a little bit more rigid so it doesn't move as much during the slip form placement, being careful about where the vibrator goes within the mold, and monitoring the speed of the slip form paver. So this shows their operation with their equipment and their findings. Now something difficult to quantify is when we design bridges, we essentially design bridges as if the parapet were not there. We assume that the parapet does not contribute to the strength of the bridge and does not really pick up the load stresses from the vehicle loads on the bridge. But in fact, a parapet is composite with the rest of the bridge, and you would expect that in positive moment the parapet's going to be in compression and it stiffens the bridge up, and then in negative moment it's going to be in tension. There have been some studies looking at this effect, and parapets that act compositely with the deck, and what that really means is if you don't find some way to break the composite action of the parapet with the deck, which may not be such a good idea anyway, you increase the overall stiffness of the bridge structure by up to 25%. This is probably pretty good because it reduces the fatigue stresses in the deck, but now you have the parapet as a undesigned load-bearing element, I'll call it that. And then when you have negative moment over the bridge piers, then you have those tension forces going in, and those could lead to cracking. Now, well, I'll get to that later. Okay. So just kind of to and of course there's lots and lots of work on cracking of concrete bridge decks, and a lot of those have to do with shrinkage of the concrete itself, the degree of restraint, curing, and so forth. So these are the 4 bridges we looked at. Canterbury Road, about 250 feet for a span. Sheldon, slightly shorter, again, 4 span. Spring Road's actually the longest, but it's only a 2-span bridge. So what you find there is that the maximum span length is twice as much as any of the other ones. And then Wagar, which is 2-span and half the length of the other ones. So each span is roughly 62.5 to 67.5, except for Spring Road. And they carry 2 to 4 lanes of traffic. And they all have, because they have multiple spans, they all have positive and negative moment regions where you might expect to see. Now, going back, kind of getting myself on the hypotheses, if the composite structural action is true, then what you should see when you walk out on the bridge is you should see a lot of cracks over the piers and not nearly so much in between the piers. For all the bridges, and again, those are 10 to 15 years old, they're carrying more traffic than expected. Probably true of just about every bridge in the United States, carrying more traffic than it was designed for. Really, the parapet condition ratings were all 1 or 2. We did find that there were common vertical crack locations, and they would form often midway between the control joints and often below or near the vandal protection post base plates. So the important thing of looking at crack patterns is if the joints are actually cracking and opening up, and the cracks tend to form halfway in between them, what that means is you probably just need to cut the interval in half, and then you'll get a joint where the crack's going to be in control of that. I mean, after all, a joint is really a controlled crack that looks better than a natural crack and should then be easier to maintain. Canterbury Road, parapet condition rating was 1 from the records. Vertical cracks at the typical locations. We did have some horizontal cracks at the top layer of the rebar, and the control joint spacing varied between 70 and 96 inches. Sheldon Road over I-71, I think this is actually the first one that the students and Dale Crowell and I went out and took a look at. Brook Park area, that has a rating of 2. Vertical cracks at the typical location. What's interesting is between, one bridge you have 2 parapets, so you have a comparison between the 2. and on the south wall you had more in between the joints, and on the north wall you had a few more that initiated at the fence post cracks, and you had map cracking along the interface of the parapets. I believe, if my memory serves me correctly, that the photo of the slide we started with, and that was titled as map cracking, is from the Sheldon Road Bridge. The joint spacing actually varied quite a bit. Towards the west end of the bridge it was an 84-inch spacing, and towards the east end it was 140 inches. And as you'd expect, once you go to the larger joint spacing, you start to see a lot more mid-joint cracks in between. And that was the most severe of the 4 bridges that we looked at in the course of this study. Spring Road over the Jennings Freeway, that had a condition rating of 1. Least severe of the bridges had inner and outer, unlike all the other ones, which have a total of 2 barrier walls, 1 on each side. This has a total of 4 because you've got an outer barrier wall, the sidewalk, and then an inner barrier wall, and then your traffic lanes. And so now you can get a good look at both the inside of the outer wall and the inside, if you want to call it that, of the inner wall, but it's harder to look at that side and that side. Generally, other than looking from a distance, we didn't use cherry pickers or anything like that. We didn't get a good look at the outsides. But from what we could tell, looking at the vertical cracks going, they were pretty much through cracks. You could follow the crack up to the top of the parapet, and then if you got to the other side, you could see it from the other side from some distance away. The inner walls tend to have more mid-joint vertical cracks, strangely enough, for whatever reason, not so much with the outer walls. Spring Road, oh yeah, the outer wall was in good condition with minimal cracking. We're on the same bridge. North wall had some vertical cracks at the expected locations, a little flaking off below the vandal protection fence base plates. South wall, again, near the fence posts, less severe. Much smaller compared to the other bridges. Control joint spacing 90 inches around the bearing pier, the negative moment region, and then 192 inches elsewhere, which is, with that spacing of the joints, it's actually surprising that we did not see a little bit more cracking there. Rocky River, Wagar Road over I-90, condition rating of 1. Again, some vertical cracks at the typical locations. What we found is that some of the vandal fence post base plates were right over the control joints. Maybe not so good, and then a 96-inch spacing. So the time then comes to list the hypotheses, put them into categories, and compare them to the evidence and see, is it a design issue, is it a materials issue, is it a construction issue, is it potentially a service or maintenance issue. So in terms of the design factors, you can look at the control joints, section properties, the reinforcement details, composites, the unintended composite structural action, and the vandal protection fence, specifically how the bases are detailed. Various factors having to do with materials. Have we, as we've seen sometimes when you change concrete mixtures, sometimes that leads to more cracking. What about the reinforcement coating, and what about the various types of sealants that might be used? What are the construction factors? And these aren't quite in order. The curing of the parapets. I understand we're currently using a 7-day wet cure. How well is the concrete consolidated? You can generally get a real good look at that, of course, as soon as the forms come off. How are the control joints built? Is concrete uniform? What about the application of coating materials? I think we talked about restraint of the parapets. And then what about service and maintenance factors? Are we somehow dealing with fatigue of the bridge? Well, if it's a fatigue issue, you would expect that the cracks would appear somewhat late in life after you've had enough truck repetitions to deal with fatigue. Normally considered, I believe under the AASHTO Bridge Code, that you don't really have to worry about fatigue for reinforced concrete elements because the stresses are generally so low. Were there impact effects? Well, we didn't see any evidence that any of these had been impacted at any point. And then, is there crack propagation from the deck or the sidewalk? I mentioned earlier, if the deck has a crack, certainly the parapet isn't going to hold it together. That will just crack up, go right up. Looking for evidence of previous crack repairs, because that tells you if there has been some effort at repairing it, and maybe it's the repair has been there a while, you can get some idea that it was a pretty old crack. What's happened with the traffic, and what about effects of corrosion? One of the things that contributes to the ugliness, shall we say, of some of these cracks is if you have any rust stains coming out of them. And in some cases, it looked like what had happened is you had cracks at the vandal protection fence base plates where you then had a little bit of corrosion and material coming out of that. If you're using epoxy-coated rebar, I wouldn't think you'd see too much evidence of corrosion coming out. In some cases, we really didn't see any particular staining. So weigh the evidence against all the hypotheses. It was believed that where we saw those horizontal cracks, a good chance was that it was insufficient concrete consolidation below that top rebar layer. And as I mentioned, I think before this study even started, there had been a change of detail from a 2-bar to a 1-bar detail, and that's likely to deal with that problem. Some cases, a control joint spacing may be too large to control the shrinkage cracks. If we are, if you have a 70-inch joint spacing and you don't have cracks in between, that's probably okay. You get up to 192-inch spacing, that's probably not close enough together to control them. And then we looked at the construction of the control joints, and one of the things that Jeff and Amy did in the course of their field observations on the bridges is they would take a card and measure what appeared to be the depth of the saw cut of the control joints. And probably a pretty common feature we came across is that they were not cut nearly as deeply as you would expect. Number of reasons for that. If it's supposed to be cut 1.5 inches deep, it's highly unlikely to be 1.5 inches deep. It's either going to be more or less. If you cut too deep, you run a risk of cutting into the rebar with all kinds of attendant problems with that, and you could get in trouble for that. On the other hand, if you cut too shallow, probably really no way of knowing, but the problem with cutting too shallow is then you may not actually form the joint. So one of the things that you can do with an ultrasonic pulse velocity is you can see if that ultrasonic wave is transmitted from one side of the joint to the other. If an ultrasonic wave transmits across the joint, and you do this in between rebar so that the wave is not traveling through rebar, if it propagates across the joint, then you know that you don't have a complete crack. If the wave doesn't propagate or propagates very slowly, which means it's going up to a bar and coming around, then that might be able to tell you whether or not the joint has in fact cracked. When is the saw cutting being done? And again, on a 10 to 15-year-old bridge, no way to know that. You have to get out on new construction to do that. We considered the possibility that the anchorage details of the VPF post base plates might lead to cracks by providing an internal restraint inside the parapet and thus initiating a crack below them. And I think District 12 has looked at some adjustments to those base plates to try to prevent restraint. We also considered whether you would have wind bending the fence and that prying action might cause the parapet to crack. But since what we're seeing at the base plates is vertical cracks, and the prying action would probably cause horizontal cracks, that didn't seem to be excessive, very likely. Do we have high water and cement content of the concrete with excessive drying shrinkage? That potentially is a possibility. What about the unintended composite structural action? I think I've already explained that one to death. And fatigue effects, if we have more traffic demand than was shown on the original construction plans, is that an issue? Again, what's the data gathered includes the photographs, the crack mapping, and mostly this is in tables in the report in terms of how many cracks we had and what the widths were, and then comparison between summer and winter, and really not a significant difference between the two. We did some rebound hammer testing, which didn't tell us very much, and we did use the James R meter, cover meter, to try to see if one potential issue was that the reinforcement wasn't where it's supposed to be. And now this is probably way too small for you to see in terms of the depth. It'll be easier to see in the report. To give you an idea, this is about 3 inches. And this is a distance from the surface of the concrete to the bar. This is 2 inches. This is 4 inches. So that's an inch, that's an inch, that's an inch. You can see that the depth is generally about 3 inches, really plus or minus no more than about a ½ inch. So by and large, those bars are where you would expect them to be. It also says you could cut 1.5 inches into the concrete, which would be here, without too much risk of hitting the rebar. But if you go to a 2-inch and you overshoot it a little bit, you might nick the rebar. And of course, you nick through that epoxy coating, you've compromised the corrosion resistance of the rebar. More fine print. The way this is presented in the report is essentially we take the hypotheses and we put supporting evidence and refuting evidence. So is it the concrete mixture? A lot of concrete gets much higher strength and higher modulus of elasticity than the specification. You might specify that you want 4,500 psi, but you may be getting 7,000 psi concrete, which may be more stiffer, therefore more brittle, more relevant to cracking. There have been some changes, I think, in the concrete mixture to reduce the tendency. The parapet construction techniques, and whether or not slip forming is an issue. We did see that the vertical cracks tended to form a very consistent pattern. The structural effects of the parapets, we do know that parapets can carry a fair amount of live load stresses due to composite action, but given that on those bridges we had a total of 12 different negative moment, I don't know, maybe not, 8 different negative moment regions, which, if this were the main effect, would have shown more cracking. We didn't see a difference between the positive and negative moment readings along the bridges. You pretty much saw that the crack pattern would remain the same pretty much the whole way. And then the details, whether or not the control joints are actually working. So one of our concerns is that the shallow saw cut, as is typically done in the field, doesn't really form a joint. Number of reasons why this may happen. One is because the crack probably tends to be shallow compared to what's specified. It terminates above the base of the parapet, and there's really no way around that. You can't get the saw blade down to the bottom. Your saw is banging against the sidewalk or the deck or whatever. The timing. You have to remove the formwork before you can make those cuts. And whether there's a possible prying effect of the fence post base plates, which we didn't see too much. One thing to look at is a concrete mixture, the composition, the curing. Another potential issue is if you could add polypropylene fibers and make it more crack resistant. And the poorly consolidated concrete I mentioned, which has been, I believe, has been taken care of. So what are our recommendations? What do you do with the parapets? Well, probably sealing would probably take care of many of the problems we've seen, at least from an aesthetic standpoint, or maybe just paint over the uglier parts. What about prevention? There has been a redesign of the vandal protection fence posts base plates, but looking at joint spacing and reinforcement continuity. One of the things is because you've got so much reinforcement going across a joint, even if you can do a deep saw cut, that reinforcement may be enough to really prevent a joint from cracking. So what if you were able to make the reinforcement discontinuous at the joint? Turns out there's a lot easier said than done. So, and then these are some things we threw out as potential ideas for future research. Review other DOT practices. Take a look at what the shrinkage and temperature effects might be doing to parapets. Take a look at internal curing, which we've had some success with in District 12, and look at maybe including fibers. So those are all different things that might be able to be done at somewhat of a low cost. In terms of our implementation plan, presenting results like today, we did have a poster presentation at TRB last year. So ideas on parapet condition evaluations, looking at design specification, maybe reducing spacing of the control joints, maybe looking at the posts, maybe something analogous to what Connecticut did where you have a control joint formed with the inserts, and then the idea of using discontinuous reinforcement. In terms of implementation, the expected benefits we expected to see from this study: reduce the frequency of the uncontrolled cracking, hopefully eliminate it altogether, but there might be some additional costs and time associated with implementation, cutting rebar to make it discontinuous. And we suggested a number of potential users and organizations, various agencies, and what the might cost would be. If you start using things like glass fiber, reinforced polymer rebar, paraffin joints, or even inserts, you might have some additional costs. And normally this is where I would be done. We finished up the study. The study was intended to end December 31st, 2012. We had turned in our final report for review. And then on September 28th, 2012, we attended the ODOT Research Summit down here and learned that ODOT would D12 considering implementing some of our findings and rather quickly. So a number of thoughts went through my head. The first one was, this is really cool because a whole lot of research work never gets turned into practice. My second thought was, gee, this is awfully scary. What if we mess something up? Wasn't too worried about that, but I do a lot of second guessing and cross-checking in myself. And then my third thought was, well, we'll probably never know. They'll go out and they'll do some test sections, and we won't really have data that will tell us what worked and what didn't. And so we proposed a couple of things. One was to take that particular project and extend it by 6 months, which is to the end of this month, for some monitoring implementation, saying if they're going to go out and do some of this, I'd like to have my students out there taking measurements and observations, and we can see if that crack shows up at 1 day or 1 week. And then we put in a proposal for a follow-on project, development, field testing, and implementation of improved bridge parapet designs, which is supposed to start July 1st. Don't know if it will, but that would be great. So let's talk then about when we tacked on the continuation, the current project, what we decided we wanted to do. We wanted to go into a lot more detail with other state DOTs and look at what are their details and maybe follow up with some individuals and find out, okay, this is what you have on your web page. Do you really use it and how does it work? and are there costs and problems associated with it. So the first step, which Lauren Hedges got started on, was to basically start going to state DOT websites and start pulling down their details and see what they did the same that ODOT does and maybe what they do differently. And then she got really busy with what I'm going to talk about, but there are at least 10 of those summarized in the revised report. And ODOT District 12 had gone ahead and put together a very interesting experimental plan, and so we wanted to meet with them and see, what are you going to do, when are you going to do it, how can we get out and take some measurements and observe what's going on. And that took place on March 7, 2013. And then develop a field monitoring plan for when these bridges, parapets are actually constructed. What are we going to do to determine the effect of some of these experiments? And then, up until the end of the month, to observe the construction of the test site parapets and begin the process of gathering data and then revise the final report. So we did revise the final report that we turned in last year. A lot of it was changes to the conclusions and recommendations, and some of these new things we put into appendices. We put in the District 12 experimental design and the field plan are all in those. So those are the goals of the continuation of the first project. I don't want to confuse you because we are still in the first project. So in terms of our, I'm getting lost here. Okay, so in terms of other state DOT details, we found 10. We're actually 10 in the version of the final report, the revised final report, which I turned in a couple weeks back, and we're continuing on. We found a few more. And then what we really want to do is we want to start getting in touch with engineers in those other states where they have what look like some intriguing details and get some ideas. How do they perform? What are your specifications, special provisions? Do you have any particular problems with them? They probably won't have any idea what they cost relative to what we do because that's going to be built into their standard plans and so forth. So then on to the new project. Again, already gave the title, scheduled to start the 1st of July for 16 months. And the idea is this will, the main thing is field monitoring to cover summer of 2013 and summer 2014. This will give us a couple of things. We have bridges that are part of this experiment that will be built in both of those summers, and this will give us a chance in summer of 2014 to look at how the different designs are performing relatively early in their age, but I think often when cracks form, they form early. So a lot of times you can see that right from the beginning. So continue our review of the other state agencies. These are their specific goals. And the idea is to come up with some improved parapet designs and/or materials and suggestions to try to reduce cracking. Develop an experimental plan, which actually District 12 did. We didn't. Meet with them to refine the plan, design for the implementation, and then monitor the bridge parapets during and immediately after construction. And as I said earlier, we've actually begun doing that because the construction schedule dictated that they were going to start some of these bridges we needed to look at as early as this month. And had we waited till July 1st, we probably would have missed a good chunk of the data we wanted to get. So there are a lot of bridges being built on I-90 in Lake County, total of 10 in fact, and each bridge has 2 parapets, and so we have a total of 20 parapets from the I-90 Lake project, and also Marginal Road over I-90, which is actually close enough to the Cleveland State campus we can walk to this one. It's a very convenient test site. And ironically, that's now the only one we haven't been to yet because we've been busy on the other ones. So we want to compare some specific parapet designs, which I'll get into in a minute, with control parapets, which are being built, shall I say, the way we've always done them, or the way we've done them for the last 2 years. So our control bridges in Lake County, this project, the 10 bridges, 3 were built back in 2012, 4 are being built this summer, and 3 more are scheduled for next year. So the 3 that were built back in 2012 are the control bridges that we can go back maybe next year and do a comparison with these revised designs that we're building this summer and next summer. These are parapets on interstate highways that are right now inside work zones. So getting to these is going to be an adventure. We haven't quite figured out how we're going to do that. Talking to the project engineer out there, he's like, yeah, I don't know how you're going to look at them either. In the 2014 construction season, we're going to have 3 parapets that are also going to be controls. So we will have those number of controls. So this year, we are looking at a total of 5 bridges out of the 11 in the experiment, which is 4 in Lake County plus the marginal road bridge. And then in 2014, we'll have 3 additional Lake County bridges to look at and finish up. So what are the test variables? What are the things that District 12 is trying to do to reduce cracking? One is modifying the concrete with polypropylene fibers. And in the experimental design, we have 2 dosages, which are 1 or 2. That should be pound per cubic yard, not pound per cubic foot. So if you want to scratch out the F and write Y on your notes, 1 or 2 pounds per cubic yard of polyfibers. And then a 3.5-inch deep saw cut, with the idea that a 3.5-inch deep saw cut, if any saw cut is going to give you a positive joint, a 3.5-inch saw cut will do that. However, the bars are only 3 inches from the surface, which presents a problem. So we have to combine that with one of 2 other alternate designs. The first one would be glass fiber reinforced polymer reinforcing bars, which would replace the steel bars, which you can cut through with no problem. The other alternative was to field cut steel reinforcing bars. Now, if you look at these, you think that going back to my expected value per bridge and say it's $7,000. Well, 1 or 2 pounds of fiber per yard of concrete, you might be able to swing that in the parapets. That might be relatively low cost. Glass fiber reinforced polymer, I actually don't quite know what those cost, but those are known to be costly. So you might think that might be a fairly costly alternative. We originally thought that field cutting the steel reinforcing bars would be fairly inexpensive, but that's because we don't do this for a living. And in fact, it's quite involved because you have to have additional ironworker personnel. You need to have the saw. It's a lot of cuts per joint. You have to cut through every bar on both sides of the joint. So District 12 has gotten change orders for this work. I think you could probably predict that when you have a cost of something that comes in as a change order, it's not necessarily the same as what the cost would be if it were included in the original plans for a lot of very good reasons. But strangely enough, it seems like maybe the field cut bars, which we thought might be a very economical solution, might turn out to be not so much, just because it's more difficult to execute. Another thing might be, what if the bars were cut to some distance less than the spacing? Well, then they might be more difficult to place. So it turns out that may be a pretty labor-intensive alternative compared to throwing fibers in a concrete truck, which doesn't have nearly as much. Another thing looking at is reducing cutting the spacing, what's called the tension zone, that's really the negative moment zone, over the bridge piers in 10 to 15 feet at other locations. So I've got some excerpts from the plans for these. This is, it's in the report. I can't remember which bridge this is, sorry. You can see that this is one of the ones that's on a skew, which I think means it's one of the first ones we looked at out on there. And we're going to define the tension zone over the pier as 12 feet each side of the pier, or 24 feet in total, and those are going to have the 5 to 6 foot joint spacing, and in between are going to have the 10 to 15 foot joint spacing. Looking at it from the side, of course, and this is a different set of details for a different bridge. In this case, it's actually 30 feet this side, 26 feet this side, 28 feet this side, 30 feet this side, so 26 to 30 feet, pretty much where you expect to have the negative bending moment on the bridge. This is the detail for the field cut bars. One thing you can see from this is a single bar. Those are double bars. Those are all double bars, so you've got 7 bars. And then you're cutting enough to leave 9 inches of steel located within the joint. So every time you do this, you've got 14 cuts, hence the amount of labor that adds up. One of the things that we can do with my graduate students on site is we can see what kind of involvement there really is in making this detail work. So we'll talk about what they're actually going to be doing in a minute. Actually, what they're doing today, which is why they're, as I think I mentioned, why they're not down here. Yeah, this is really fine print. Essentially, this is the estimated schedule. It's in our draft final report, and the one thing you know about all estimated construction schedules is they tend to migrate in this direction. So we have, but what is really, it seems that unless some slips into August, the bulk of this is from a couple of days ago through about the end of July on 5 bridges. Now, the bad news for the grad students is they're going to get run ragged. The good news is they're going to have pretty much all the data for their theses, most of it, and then they can spend the winter writing it up, except for the things. And what we're finding is like there's a delay in fabrication on Marginal Road. This is the latest I had. New expansion joint, so now the deck might be poured into July. One thing that you can't do parapets before you pour the deck. So once the deck is actually poured, that really narrows down our window when we're looking down the parapets, and that's a key piece of information that we're monitoring with our project engineers for the 2 projects. Jim Farrell, Mark Sakian from District 12, been out visiting with Jim. So what's the field testing plan? Well, per parapet, the research team students will end up making a minimum of 5 visits. Now, the nice thing, because some of these are close together, some of these can be grouped together, but you can imagine this ends up being a lot of labor. If you have 22 parapets times 5 visits, that's 110, so that's a whole lot of work. First thing I want them to do is pre-construction observation. Actually, these go together. The steel reinforcement location, if they are doing the field saw cuts, what that looks like, mostly making sure the reinforcement's where it is. And then they also install maturity sensors for temperature monitoring and talk to people not to cut the cords on the maturity sensors. On the day of placement, they're looking at weather conditions, taking a couple of small samples of concrete. The main reason we do that is not to get strength test results, but I want to be able to calibrate the ultrasonic pulse velocity wave speed, and that's a whole lot easier if I got a cylinder back in the lab. And we're trying to do this to be as unobtrusive as possible. And then saw cutting, which on the last bridge was 1 day later, looking at what the timing of the saw cutting is compared to the placement, what the actual depth of the saw cutting is, and probably I'm thinking with 2 students watching them, they might actually do the full 1.5 inches as opposed to what they already do. And then when you take the forms off, they can look at consolidation if they have honeycombing, and that gives them a chance to get some idea of whether the concrete's cracked before you even cut the joints. What they reported back to me from yesterday's observations is they did not see any cracks at the time of saw cutting. Then the curing goes on for the next week, and then they come out after that when that's removed. and see if cracking occurs then. And then, it's not on this slide, and actually that wasn't on the slide. At some point, we need to do a large-scale review where we go to a lot of these towards the end of the project and see what the final end state of the cracking on all these parapets. So we're doing maturity data collection, and normally maturity is used for strength prediction, but in fact we're using our maturity sensors for temperature history and to look for thermal shock when the curing comes off. We're going to investigate whether joints have cracked using the James R meter for reinforcement depth, location, continuity, James V meter for continuity, and whether you actually get a signal across a joint or crack, and then the post-construction crack survey, and maybe then is when we go back to the 2012 bridges and see how they ended up. So on Payne Creek, these are my students who are out working hard today. Amy Caliban on the left, you can see how dense the reinforcement is. She's tying in a maturity sensor, and we have to have that cord fed out of the formwork. Hopefully nobody cracks it, because you take a PDA and you hook it up to 2 leads coming out of that, and that gives you the temperature history every half hour since the time of concrete placement. This, I believe, is Lauren Hedges. It's kind of, looks like it kind of small, and this is after the formwork is on. Checking those, and you can see we get some rain from time to time, hence working around the construction. Yesterday, they were out at 6 a.m. for construction, came back to the office around 2 o'clock, looked a little tired. Hopefully they're getting enough water and sunscreen. So that's essentially what we're doing for the next part of the study. Standard acknowledgments that you have, and I think I've left close to 20 minutes for questions.
Length considered?
Good question. For the 4 we've looked at, these are all steel bridges, so you don't have the issue of flexibility of steel versus pre-stressed concrete. We only have the one that has a different span length, which has twice the span length, and therefore that bridge should be a whole lot more flexible. So I'm going to say no, but that's a real easy thing to look at because we have that one bridge against these. The other thing is we have these different span lengths of these bridges, so we can look at that as a variable as well. That makes a lot of sense. A bridge that moves more because it's more flexible is going to have a greater risk of structural related cracking.
Another question, are all the parapets in the CSU add-on study hand-formed and poured, or are some being slip-formed?
I don't think District 12 does slip forming. My understanding, obviously you can see from the picture these are hand-formed. I don't think any of these would be slip formed, but I can check. My understanding is none of them will be. The entire web, I get only 2 questions? Okay. Other questions?
I do have one.
Could you get the mic, please, so our TV audience can hear?
Okay, hi. I do have one question. At one point, I think the slide pointed toward excessive longitudinal restraint. Did you mean the deck? In other words, the deck's poured first in sequence, locked up, as a single mass, and then you pour a parapet on top of it, and the parapet wants to shrink on that plane, the interface between the two. Therefore, I assume more shrinkage puts higher tension stresses in the parapet, and I guess telltale sign would be, and I don't know, are the cracks forming from the deck up, or do they seem to be coming from the top down? If they're coming from the deck up, it would seem to be tearing from the bottom, and that would make sense as to why then.
Yeah, good question. I don't, to my knowledge, there's no positive, let me go back and look at this. There's no real positive separation between the deck and the parapet. If you look right there, that's going to give you excellent bond. I think I did ask them to look at whether they were wider at the bottom than at the top. I don't think we had any. They're pretty fine to begin with, so it's hard to tell.
I guess, yeah, that's good observation, or good inspect.
Yeah.
If they make it clear to the top, would be if they're so small they're immeasurable. Then I guess if they don't make it clear to the top, then they had to start at the bottom.
Yeah. I don't, and I'm trying to think how many we had that essentially ran out. I think the bulk of the ones we saw were continuous top to bottom, and seemed to be the same width top to bottom. But clearly, that's something that we can take a look at this develops. I know that's one we talked about. And the other telltale sign, of course, is if it occurs, as I mentioned earlier, if it occurs at the same place as a deck crack. But one of the things is the deck is going to provide restraint to the parapet. There's no question about that. And I honestly don't think there's any practical way to break that restraint and provide any kind of isolation joint. So maybe what that suggests is, given that you've got that much restraint on the bottom and a fair amount of restraint from the steel, that suggests maybe a more positive effort to form a joint, either the deeper cut or even go back to some type of detail where you actually physically have a piece of material that is attached to the rebar cage that forms a joint. Obviously, there's a cost associated with that. Again, I'm now tempted to try to see what frequency we have of this problem, to the extent that we actually have to prematurely repair the parapet, because that will give us an idea of what the expected value is, and maybe the best thing to do is paint over the ugly. Okay, I think, who's next?
Is it my understanding that the first 4 bridges you did were steel beam bridges?
I think that's pretty much about all we build up in Cleveland.
You don't use precast reinforced beams?
None of those were, and it's, from my observations driving around Cleveland, it's much more steel up that way. Okay. So one of the things that has not been considered, and I don't know how much in effect, would be whether you would see less of this if your girders are pre-stressed concrete, because we've restricted our study to essentially District 12.
Yeah, the reason I ask that is in Montgomery County, most of our long span bridges are precast reinforced concrete up to 100 feet, 110 feet.
Yeah.
So I was just trying to understand whether there'd be any difference.
We're a steel city. I guess I'd put it that way. Which, for a guy who studies concrete, sometimes is not so great. But what you going to do?
A question of the saw cuts that were in the existing parapets you looked at. Was there any determination how many of those actually caused a crack to occur at that location? Or initiated a crack because of
I don't know that we actually really use the UPV across those to try to determine them. I mean, it's kind of tough to tell. I mean, you put in a card and that stops at a certain depth, but you don't know if that's because that's as far as it goes, or then the crack forms but it's jagged enough so that the card won't go in.
So you weren't allowed to take any cores or anything to determine that?
We didn't ask. They look bad enough as it is. We got core in these things that look awesome.
And then my second question was, where the cracks were, was there any determination of how those lined up with the vertical hairpins directly, behind that? Was there any correlation to a crack versus where the vertical rebar was?
Didn't really look at that. You see how closely spaced the verticals are. But yeah, is it between or right at? Well, we could find that with the rebar, with the R meter. We can determine if that's where it happens. Good question. Hopefully the recording. Unfortunately, the students are too busy to watch this either, so they'll have a chance to go back and review, and maybe these are some things we can bring in the next part.
did think of one other one. I can think of one bridge that I've seen built in 2 phases within the same construction season. The first parapet of which, I can't remember if it was left or right, but got put on, and noticeably after 5 years, I think the last time I saw it, one has a lot of cracks in it and the other does not. The other got poured later in the year. So if temperature in combination with shrinkage would have something to do with that, it might be good to look at which direction the temperature is going. You may mention that. I just don't know if you've actually got it.
The one that was poured first or second has more cracks?
I believe, from memory, it's the second one. In other words, the one going into winter. But it wouldn't make as much sense. So.
Well, the other thing is you go back to that Quebec study, and their hypothesis is that some of it was caused by green concrete and traffic being carried on the other half of the bridge. And the evidence of that would be the first half, where there would be no traffic, would be fine, and the second one, which would have been poured when there's traffic on the other half. So that would consistently show that the second half would be the one that would have more cracking. So that's something, because all of these are basically being built that way, one half and then the other half. So that is potentially a factor. If you've got vibration from vehicles going on while the concrete's green, then there is a chance of that.
Okay, thanks.
Okay, you got another internet question.
Okay.
So is the study suggestion that slip forming and ham forming a parapet provides a similar end product? And if you are adding other variable change order, why are you not looking at the effect of this variable?
We're not suggesting that because I really don't know. I think I want to say I think everything we've looked at in our area has probably been hand formed. I have no idea what sort of change order would be involved in having these slip formed, and I don't know how interested District 12 would be in. So I don't know that that's really a variable we're looking at. It just wasn't one we could work. And as it is, if you look at the number of different variables we're looking at, even though we've got 22 samples, a statistician would tell us you don't have anything at all. So there's real limits to what you can vary in a study and being able to make any sense out of the results. 22 is not a whole lot of data points, particularly when half of them are controls. It's an interesting idea. We just aren't set up to answer the question of slip forming versus hand forming. Long trip for the mic.
You talked a lot about field insert joints, but that didn't show up in the continuation report. I was wondering why those field insert joints weren't considered as a potential solution to all the issues you have with getting that control joint to work.
I think maybe if we talk to enough states that have used those and are happy with them, we might suggest that those be looked at in 2014. Obviously, the 2013 season is a runaway horse, and we're barely hanging on. That is something that we would like to look at. I'll say that essentially we didn't, in our original report, we didn't really push hard on that, and I think District 12 rightly set up the experiment in terms of what they thought they could practically implement on projects that had already been bid and let. And, we did make that an observation of a paraffin joint, but, we need to, one of the things we want to do is do a little bit more work and see if these are used, where they're used, what the associated details. Certainly if you have to combine that with field cut rebar, the cost might be way out there. So I don't know. In a way, I guess I have to, not that I'm distancing or not that I disagree in any way with the way District 12 set up the experiment, because I think it's pretty well done, but we pretty much came on with the experiment they set up, and what we suggested was, given that you have an experiment underway, this is our plan for gathering and analyzing the data, so at the end of the day we know what worked and what didn't. Because a difficulty you often have, and this goes back to my dissertation research in El Paso in 1996, is a DOT will fund a study, they'll get a result, they'll go to implement the results. Now the studies run out, and so the two pieces that end up missing are whether it gets put in place the way the researcher envisioned, which is not what happened in El Paso, and the work, which actually is quite a bit of work when you implement something to see whether or not it works in comparison to other things. So I'm very glad they set up the experiment. I'm glad they set up the experiment the way they did, and we're really happy to be working with them to gather the data. A lot of things could be done on this issue depending on how big a problem others think it is. And I think there are, and we may, based on our review of other state DOT details, we may suggest some things that might be tried in the future. Still 4 minutes by my watch. I don't know.
At this time, we're going to conclude the presentation. We thank you all for participating. This presentation has been recorded. It will be available on the research website in about a week, along with a PDF version of the PowerPoint. And within the next few weeks, maybe a month, the actual final report that Dr. DeLotte has been referencing will also be available on our website. If you come up with additional questions you would like to have Dr. DeLotte answer for you, you can email those to research@dot.state.oh.us, and we will forward them on to him. Thank you very much for participating.